In this video, we are going to be doing a couple related rates examples involving spheres. I will be linking my other related rates videos below in the description. So this says air is being pumped into a spherical balloon so that its volume increases at a rate of 200 millimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 40 millimeters? So my first recommendation is to draw a picture. A lot of times we will use it, sometimes we will not, but it's good to have a visual. And then I like to write down what we know and what we want. So we know that the volume of the sphere is increasing at a rate of 200 millimeters cubed per second. So I'm going to say dV dt, because my volume is increasing at a rate over time, is 200 millimeters cubed per second. Now I'm making the 200 positive because my volume is increasing. If my volume were decreasing, I would make that 200 negative. And then it says, how fast is the radius of the balloon increasing when the diameter is 400 millimeters? That is what we want. So I want the rate that the radius is increasing, so dr dt. And I want it at the moment when the diameter, I don't have to write it out, diameter is 40 millimeters. So what we need is we need an equation that relates volume of a sphere with its radius. And so we would use our volume formula for a sphere, which is 4/3 pi r cubed. Once we have our equation, we are going to take the derivative of both sides of the equation with respect to time. This is going to involve implicit differentiation. I will link that video below as well. But we are taking the derivative with respect to time, so we're going to have dV dt on the left. On the right, I'm going to have 3 times 4/3, so that's 4 pi r, decrease your exponent, r squared. We need the derivative of r with respect to time, so dr dt. Once we have taken the derivative with respect to time, then we can plug in. You always want to take the derivative first, plug in second. So I'm going to say when the diameter is 40 millimeters. Now I want you to notice that my dV dt has r in it, but we know the diameter. So in this case, I would say, let's say radius is 20 millimeters. Radius is half of the diameter. And that way we will be able to plug in. You also could have changed your dV dt to be with respect to diameter. Either way is fine. So my dV dt is 200, 4 pi, my radius is 20, and we are solving for dr dt. The rest is just solving this equation. So I have 200 equals 4 pi times 400 dr dt. I'm going to solve for dr dt. That's 200 over 1600 pi, and we can simplify, divide by 100. I'm going to divide by 2. I'm left with an 8 in the denominator. So my dr dt is 1 over 8 pi, and we need our units, so it's going to be millimeters per second. And that is our first example. We have one more example. It says a spherical balloon is being inflated at a constant rate of 6 inches cubed per minute. When the radius of the balloon is 5 inches, how fast is the surface area of the balloon changing? So same thing, I'm going to draw a picture. We have a sphere. I'm going to write what I know and what I want. We know that the spherical balloon is being inflated at a constant rate of 6 inches cubed per minute. So if a balloon is being inflated, that means volume. So my volume is increasing at this rate. If you're not sure whether it's volume, you can also look at the units. Inches cubed per minute is a volume. So I'm going to say dV dt equals 6 inches cubed per minute. Same thing as the first example, I'm making that 6 positive because my balloon is inflating, so my volume is increasing. If my volume were decreasing, I would make that 6 negative. And then what do we want? We want to know how fast the surface area of the balloon is changing. So that's going to be ds dt. And we want that when the radius of the balloon is 5 inches. So I'm going to make my surface area equation for a sphere 4 pi r squared. From there, I can take the derivative with respect to time on both sides. Same thing, this is going to be implicit differentiation. ds dt equals, I'm going to have 4 times 2, which is 8 pi r, and then I need the derivative of r with respect to time. Now I want you to notice that I'm solving for ds dt, and then I have dr dt, but I don't know dr dt, I know dv dt. So we're going to have to do some extra work to figure out what dr dt equals. So I'm going to do a second equation, but now I'm going to use dv dt and dr dt, or volume and radius. So I do know radius of a sphere, I do know volume of a sphere, 4/3 pi r cubed. I can take the derivative on both sides with respect to time. dv dt equals, same thing as the first example, 4/3 times 3 is 4 pi r squared. Derivative of the radius with respect to time. From here, I'm going to plug into my dv dt. I know that dv dt is 6. I have 4 pi. My r, I'm plugging in when r is 5 inches. So I'm going to plug in my 5. And I want to solve for dr dt. So I get 6 equals 4 times 25, which is 100 pi dr dt. So that means that dr dt is 6 over 100 pi, or 3 over 50 pi. And that is what I'm going to plug into my dr dt. So moving back to my first equation, I have ds dt equals 8 pi, my r is 5, my dr dt is 3 over 50 pi. Last thing we need to do is simplify, so I'm going to say ds dt equals, let's cancel out a 50, we get 10, cancel out a pi, cancel out a 2, we get 4 and 5. 4 times 3 is 12 over 5. We need our units. This is going to be surface area, so area is going to be inches squared per minute. And that is your answer. So those are a couple related rates problems with spheres. Like I said, I will put other shapes and other videos in the description box below. Thank you for watching.